Hello everyone. Welcome back to our channel. In our last video, we reviewed the key ideas behind logarithms and their rules, and we also explored an interesting telescoping series involving logarithms. Today, we're going to look at another fascinating problem. The question is, how many real numbers satisfy the equation shown on the screen? On the left side, we have a sine function whose period is 2 pi over 20 pi, that is 0.1. On the right side, we have a logarithm with base 20. At first glance, this equation looks pretty complicated. So, how do we solve it? In this equation, one side is a periodic function, and the other side is non-periodic. At first glance, it might feel impossible to figure out how many solutions there are. But if we sketch both functions together on the same graph, something interesting happens. The logarithm curve intersects the periodic sine wave at several points. And each intersection represents a solution. A root we're trying to find. As you can see, the sine curve forms alternating upward and downward humps, and the intersections with the logarithm curve occur only on certain humps. So our job is to identify which humps are up, and which humps are down, and then determine where the intersections happen. Once we sort that out, the number of solutions becomes clear. Let's go step by step and uncover the structure behind this problem. First, the argument x in the logarithm must be positive, which already restricts the domain. Next, the sine function can only take values between -1 and +1. Applying this restriction to the logarithm, we find that x must lie between 0.05 and 20 including both endpoints. So, all solutions to this equation must lie in the interval 0.05 to 20 and inclusive. Actually, the value 0 gives us a clean way to see where each upward hump transitions into a downward hump. So our next step is to locate all the zeros of the sine function within our interval 0.05 to 20 and inclusive. We find that the sine function is 0 precisely at the integer value equal to 1, 2, 3, up to 400. Yes. We finally see that all 399 zero intervals, from the integer equal to 1, up to 399, allow us to determine exactly which sine humps are up, and which are down. Between consecutive zeros at the integer k over 20 to k plus 1 over 20, the sine function forms a single hump, either entirely above the x-axis or entirely below it, reaching the positive 1, or the negative 1 at the midpoint. To better understand the behavior of the two functions, let's look at their difference as shown in the screen. At the zeros of the sine function, where x is equal to the integer k over 20, the sine term vanishes, so the difference reduces to just the logarithm term, with a minus sign. This lets us read off important information directly at each zero. From this, we observe three key facts. Number 1. When the integer is less than 20, the logarithm is negative, so the difference is positive. Number 2. When the integer is equal to 20, the logarithm is 0, so the difference is exactly 0. This gives us one solution at x equal to 1. Number 3. When the integer is greater than 20, the logarithm is positive, so the difference is negative. In the graph, we plot this difference function, and you can clearly see the three key facts we just described. Now we arrive at step 3, performing a sign analysis on each zero interval. When the integer is less than 20, the logarithm value is negative. If the hump is positive, the sine curve rises up to the positive 1, then the entire difference function stays above 0, so there are no roots in that interval. If the hump is negative, the sine curve dips down to the negative 1, then the midpoint gives a negative value, while the endpoints give positive values. This guarantees two roots in that interval. For the odd integers k equal to 1, 3, up to 19, there are exactly 10 negative humps, each producing 2 roots, except at the integer equal to 19, where the upper endpoint lies at x equal to 1, giving only one distinct root. So, on the interval 0.05 to 1, we obtain a total of 19 roots. As we mentioned earlier, there is one distinct root at x equal to 1. Next, when the integer is greater than or equal to 21, the logarithm value becomes positive. So at each 0 of the sine function, the difference function is negative. On the positive humps, that is, for the integer equal to 20, 21, and all even integers greater or equal to 22, the midpoint has a positive value for the difference function, because the logarithm value is less than 1 whenever x is less than 20. Since the difference function is negative at the endpoints and positive at the center, each of these intervals contains 2 roots. With one exception, the integer k, equal to 21, contributes 1 root. On the negative humps, all odd integers greater than or equal to 21, sine reaches negative 1. At the midpoint, making the entire difference function negative. This means there are no roots in these intervals. Thus, the even integers from the integer equal to 22 through 398 produce exactly 189 positive humps, each contributing 2 roots, for a total of 189 times 2, equal to 378 roots. Now we come to the last step. We add up the total number of solutions based on our earlier analysis. For the odd integers, k equal to 1 up to 19, we found 19 roots in total. For the integer, k equal to 20 and 21, there is 1 root each. For the even integers, k equal to 22 through 398, the positive humps contribute 378 roots. Putting everything together, we obtain a total of 19 plus 1 plus 1 plus 378 is equal to 399. So, the equation has 399 real solutions. The key insight is to restrict the logarithm's domain, divide the interval using the sine zeros, analyze the sign of the difference function on each hump, and then count how many intervals produce intersections, leading to exactly 399 solutions. What do you think for this problem? The solution? Key insight? Leave a comment below. And don't forget to like, share, and subscribe for more fun math problems.